To begin studying the definite integral, we started our journey by thinking about the area under a curve. Formally, if y equals f of x is non-negative and integrable on a comma b, then the area under the curve, y equals f of x over a comma b, is defined to be the definite integral from a to b of f of x dx. This is one of the most important statements. It lets us think about all of our definite integrals as areas if our functions are non-negative, right? Starting at 0 and going up, or just touching somewhere, but always positive or equal to 0. And if we had a function that was below the x-axis, right, we could imagine taking the absolute value, we get a positive area, and that tells us that the thing hanging down below would be a negative value. But it also opens the door to evaluating some integrals that we probably don't want to use Riemann sums and limits of Riemann sums to do. Right, we're good with using Riemann sums and those limits when it comes to linear functions, quadratic functions, and cubic functions because we had special formulas for that. Now, I could break this up into two integrals where this is a linear function and use Riemann sums. And this one I don't think I'd have any luck with if I wanted to use Riemann sums. But fortunately, if I graph the integrands, I'll be able to use the fact that area and the definite integral are the same for non-negative functions. The graph of absolute value between -2 and +2 looks like this. And so the definite integral should correspond to this area. And what I see is a non-negative function bounding area in two triangles. I should be able to tell you the value of this definite integral by finding the area of those two triangles. So over here, that's 1 times 1 divided by 2. The area would be 1/2. And on this side, the base is 2 units long. The height's 2 units long, so 2 times 2 is 4. Divided by 2 is 2. So this definite integral would be 2.5, 2.5 or 5 halves. So I was able to use known areas to evaluate a definite integral. Looking at number 2 here, I'm hoping you recognize that integrand, but just in case you didn't, I could imagine writing it down as a function, squaring both sides. And if I add an x to both sides, I see I get x squared plus y squared is equal to 16. And then I realize that this would be the top half of a semicircle with radius 4 centered at the origin. And so I can also evaluate its definite integral because I have a non-negative function bounding this area by finding the area of that semicircle, which would be pi r squared over 2. So pi, the radius is 4, so 16 over 2, that area would be 8 times pi. These kinds of problems are very common on homeworks, tests, labs, and final exams to make sure students have made a connection between the definite integral and area under a curve. Never try to do these using a Riemann sum, and even after we learn the material in section 5.4, using the areas are still preferable for finding these particular definite integrals rather than using what we'll study in 5.4.